So let me tell you about the plan from here on. Okay, so we'll continue from here, but let me tell you what we'll do. So for the exam, we'll have it a week later. Since we also had our previous exam a week later, then we'll just do this. So we'll have exam 2 on Tuesday. Not this coming Tuesday, but the following one. So 4/20. So that was the original tentative date, the 4/13, which is next Tuesday, but we'll have it a week later. And we will include inclusion exclusion. Which was section E in the combinatorics book. And we'll have sections A, B, and C, which is basic graphs, isomorphisms, and bipartite graphs. Which is graph theory, sections A, B, and C. And we don't have enough time for wikis this time. We'll go back to wikis for the last part of the semester. I'll have some. So we'll have some problems assigned for you to study for this exam. What I really want to do is to have a quiz or, for the isomorphisms part, or probably for the. I cannot include bipartites just yet because we haven't started. So maybe we'll, instead of having the quiz for this weekend, let's just have the quiz for this weekend. I won't include bipartite graphs, so we'll have a quiz on isomorphisms. I'll tell you more about it this weekend. And I'll assign to study for the exam. So this will be quiz 6, right? I think.
How many questions is a quiz going to be?
We'll do it as the inclusion exclusion. So I'll give you a list of problems from the isomorphisms for isomorphisms. You try them and you'll get one at random.
Oh, okay, thank you.
Which reminds me that I don't think I have uploaded my solutions to. Did I? No, I don't think I did. My solutions to the problems in quiz 4.
No, I
don't think so. I have them all, but I'm not sure. Give me 1 second.
Is the homework been assigned yet? Because last time I checked in Canvas, I didn't see any homework for A or B or anything like that.
No. So I'll give you a list of problems for both for the quiz and for the exam. Because we haven't finished. Oops, sorry guys.
Okay, so the homework hasn't been assigned yet. I'm surprised we're getting an exam already. train so soon
Well,
unless this exam's going to be very short.
Until the 20th. The exam is until the 20th, right? Today is the 8th.
True. I just mean that the first exam, it was like a few months before we took it. So.
Yeah, but the semester will be over on the 13th. That's our last meeting of May.
So things are picking up. Well, I guess hopefully by taking this exam and final, huh?
That not really, Sean. The sections, the combinatoric sections that we went over are much more complicated than what we're doing right now for graph theory.
Oh, wonderful.
The rotations and distributions when we got there. Yeah.
Visual diagrams I thought was a little easier for me versus probability problems.
Okay, so here we go. I'll upload this. So I have these solutions for you for quiz 4, but for some reason I don't have them in there yet. So let me just write it down to make sure I have them there today. Okay, so I'll upload this. I'll give you it's going to be a small list of problems for isomorphism. So I'll show them to you right now. We're going to finish with that section. And then I'll also make a list of problems for the bipartite graphs section. That's also a very short section. So okay. So here, I'll assign the list. And I'll upload. So I already made a note for myself. I'll upload answers to quiz 4 so that you can also, that goes with inclusion and exclusion, so you can also use them to study for the exam. Okay? So that's the plan. And actually, we're going to finish with bipartite graphs on Tuesday next week, and we'll start the next topic before the exam. But that next topic, which is planarity, section H in the graph theory book, is not included on exam 2. We will have it on exam 3. Okay? So let me just write here, because someplace in the syllabus we have planarity. Planarity is the section H will be included in exam 3. Just to clarify, we haven't started that. We will start it before we take exam 2, but it won't be included there. Right? Let me see if there's something in the chat. Okay. Oh, thank you, Shane.
Exam 3 is just the final, correct?
Yeah, exam 3 is not. So we don't have a cumulative exam. It's like a midterm. It's our third midterm, but it's during the finals week. It's replacing the exam. Mm-hmm. All right. So we'll do that. Any questions about this? Mm-hmm. So
any question when the quiz was due?
I usually prefer Saturday, but last time I got a couple of emails asking to move it to Sunday, so we can just leave it. I know that there are some people working on Saturday, so we'll leave it to Sunday. Okay. But this one will be due Sunday, and I don't know if you noticed that I also extended the time for that previous quiz. When you open it, it tells you how much time you have left. So I'm trying not to make it, I don't want the time to be the issue. So I'm trying to give you a little bit more time for those quizzes. So I'll do the same for this quiz number 6.
Thank you.
Anyways, you're welcome. So that should be, again, there's not much. We have finished with the presentation. We have finished with basic graphs. We're in the middle of isomorphisms, but essentially we cover everything that's there. We just need to practice, and that's what we'll do today. And the bipartite graph section essentially has one theorem, definitions and things with one theorem. So it's also a very short section. So we're essentially done with the material. We're almost done. We're not done, but we're almost done with the material for the exam. So it should be fun. And then we'll talk more about the last part of the semester afterwards. Anyways, so this is where we were last time. This is section B, the isomorphism section. And again, we essentially have to practice now. How do you prove or that two graphs are isomorphic or that they're not isomorphic? If they're isomorphic, you have to show the labeling, relabel the vertices of at least one of the two graphs so that they become equivalent. Now, that's the only thing that you need to do. There is no arguments. No, you don't have to explain anything. If you are just relabeling just show me the labels, right? That's all you have to do. However, you have to figure out how to find those labels, and so that's what we want to practice. If you want to show that two graphs are not isomorphic, that's harder. In general, that's harder. And so we're learning things that we can say. This was one of those examples. If they are isomorphic, they essentially satisfy everything the same. Same number of vertices, same number of edges, same degree sequence, same number of connected components, same complements, same everything, because they're essentially the same graph. Right? So if you find one of those things that they are different in, then the graphs are not isomorphic, and that will be your explanation of why they're not isomorphic. So let's practice with some of these problems. One nice practice is to try and find all the non-isomorphic graphs with a certain number of vertices. So here you have the graphs for one vertex. There's only one graph. Two vertices, you can have this one that has two components, or you can have that one that has only one component. So they're not isomorphic. And then you have the ones with three vertices. So here, three components, or better yet, I guess it's better to try and find them by the number of edges. We're gonna do this for 4 vertices. So here you have one edge, right? The ones with one edge, the ones with 2 edges. There's only one of those, and then the one with 3 edges. Mm-hmm. So that's one way to organize your counting by the number of edges. Huh? We're going to find now the ones for 4 vertices, and we're going to try to classify them somehow. And that goes with these 3 problems, 3, 5, 16, and 17. Mm-hmm. But I'm just going to open another page. So I'll say all non-isomorphic simple graphs with n equals 4 vertices. Okay. So I can have, I'll separate them by the number of edges just to have an organized way of counting. I'll separate by the number of edges. So we're going to start with 0 edges. Mm-hmm. So I have this one. And then the ones with 1 edge, I only have 1 of them. And it doesn't really matter where I draw the edge. All of them will, any way that I draw it, they will be isomorphic. 2 edges, I actually can have two of them. I can have one where the edges are incident to the same vertex, or they share a vertex, and one where they don't. Mhm. So these graphs are not isomorphic because one has a component with one vertex and the other one doesn't. That could be one way to say why they're not isomorphic. Huh? Another way, they have different degree sequences. They're not isomorphic. Mhm. And, if you look at any other graph with four vertices and two edges, it doesn't matter how you do it. Let's say if I have, I don't know, this one, that's four vertices, two edges. This is going to be isomorphic to one of the two that I already have. This one has two components, right? This one has this component, and from these vertices, I cannot go to the other two by paths, right? So this one has two components. And so now you can label, this one to match to match that one. Yeah? So you can label AB, AB, CV. And so it doesn't matter which drawing you give me of a graph with two edges and four vertices, I will be able to match it isomorphically, find labels to make it equivalent to this one or that one. Mm-hmm. And so three edges, I can have a one like this. I can have one like that. A vertex of degree 3. I can have a vertex of degree 3, and that's the only way that I can do it. But if I don't have a vertex of degree 3, then all the vertices have degree 2. This is one way to have all vertices of degree 2 or 1. And then I can also have the path, that one. If I only have vertices of degree 2, then I can get started. I can get started with one vertex of degree 2. It doesn't matter which two edges I select. And I still have to add one more edge. So I can add this one, that will give me the last graph that I have. Or I can add that one, which will give me the first one that I drew with three edges. Or I could draw this one, which gives me the one below. Or I can draw this one, which gives me that one. Right? Those two are isomorphic. Mm-hmm. Or I can draw, which one am I missing? One, I drew this one, that one, that one. I think I drew them, all my four possibilities, right? That one, this one, or this one. And we have them up. Mm-hmm. So those are my three possibilities for three edges. Now I can keep counting, but the more edges that I have, the more possibilities I have, right? So I'm gonna get some help from the complementary graphs, the complements, mm-hmm. because the complement, for example, the complement to a graph with the complete graph with four vertices has 6 edges, and I actually want to draw it here. See this one, is the complement of that one. This one has 6 edges. This one is the complement of that one. So any graph with 6 edges has a complement with 0 edges. And I already know all the ones that have 0 edges. So there's one for each. So I know that there's only going to be one with six edges. And same thing with 5 edges. Anything that has five edges is a complement to one with 1 edge. Remember that the complement is just whatever is not there, right? So the complement of that one is the one in red. That's its complement. So it's going to be 5 edges, right? So I can draw it here separately. So that's a complement. And there's only going to be one. We only have one with 1 edge, so we only have one with 5 edges. But it's easier. I don't know about you, but to me, it's easier to understand that there's one of these than to understand that there's one of those, right? So that's why I'm kind of making use of those complements. Okay. I also have the ones with 4 edges, and so I can look for the complements of those graphs that I have above. So this is the complement. Well, I could do it here with a different color, but I really don't want to overlap. But that's what I'm doing. I'm just taking all the edges that are not in the one above. Okay? And if I take all the edges of the one above here, that gives me that, like a square, that a twisted square, I guess. Oops. So it will give me this one, which, by the way, and I added here as another one of those examples, is isomorphic to just the square, this isomorphic. These are C4s, right? So 1, 2, 3, 4, 1, 2, 3, 4. Those are C4s, drawings of C4. Okay, so I have those. And then these ones are actually a graph with 2 edges. Its complement has 3 edges. What happens? So they're all going to be in this same group. And actually, you see, what's the complement of the first one? The one below, right? So these are complements. Mm-hmm. And this one is self complementary, I guess. If you draw the complement, it's another path. It's a process, but it's also a path. They are the same. I can also write it here. This one and this one are isomorphic. I can label them 1, 2, 3, 4. 1, 2, 3, 4. Mm-hmm. So that one is self-complementary. So there are 11 of them. So there's a problem after that says to find all the graphs with 5 vertices. I think that would be helpful for you to understand this idea of what's isomorphic, which graphs are isomorphic. But this would be the one for 4. Any questions?
So you are saying to show it's isomorphic, basically if you show it's self-complementary, that's another way of showing this is isomorphism?
Well, I'm trying to find all the ones. I'm not proving really right now the typical problem for they give you 2 graphs and they ask you if they're isomorphic. I'm not doing that, right? What I'm doing is I'm trying to find all the graphs that are non-isomorphic to each other. So any of these 11 graphs is not isomorphic to any other graph in here. All of these are non-isomorphic. Take any two and they're not isomorphic. And there are several reasons why they're not isomorphic. I would say pick two at random. That one and this one. They're not isomorphic because they have different number of edges, right?
Okay.
That would be the reason. If I take that one and that one, not isomorphic, they have different number of edges. This one and this one, not isomorphic because they have different degree sequences.
Mm-hmm.
So that the only possibility that they could be isomorphic is if they're in the same group, same number of edges. But these two are not isomorphic because they don't have the same degree sequences. These two are not isomorphic because they don't have the same degree sequences. These two are not isomorphic because they don't have the same degree sequences. But this is an exercise of, even though we're not saying all those things all the time, this is a way of using all those ideas at the same time to classify and find all the essentially different graphs with 4 vertices. And here in my notes, I was just telling you how we really have them all with just some examples, Here I'm actually showing that these two are isomorphic. Here I'm actually showing that these two are isomorphic by giving the labeling.
So it's, excuse me, it's not that it has an isomorphism, it's just that it's not isomorphic with any of the other things that we derived?
Yes. So all of those are not isomorphic to each other.
Okay, because like that lot.
And if you give me any simple graph with 4 vertices, just give me any drawing, I'll find one in this list that's isomorphic to that one. So just come up with your favorite drawing of a graph with 4 vertices. It doesn't matter where the vertices are, 1, 2, 3, 4, and just draw any graph you want with those 4 vertices. Maybe I want to draw, I don't know, this one. I don't know, that one. Your favorite graph. Well, you should be able to find one here that's isomorphic to that one.
Yeah, that's,
so let's see.
I just get confused a lot with the definitions because when I see it as saying a non-isomorphic graph, it's just, I think that the graph that I'm coming up with, there is no isomorphism to it, but it's not really that. It's in as much that.
Okay, I understand, Scott. Yes. And I completely see how that can be confusing. So when we talk about isomorphic graphs, we're talking about a pair of graphs, right? So 2 graphs are isomorphic if you can relabel them to make them equivalent, right? 2 graphs are not isomorphic if you cannot relabel them to make them equivalent, which, again, is harder to show. You will need to find that they have something different, like different sequence, different number of vertices, different something, right? And that's harder. Anyways, when we say find all non-isomorphic graphs, what we mean is find, imagine that you have all of the graphs with 4 vertices, which seems to be infinitely many, right? And then you classify them by isomorphism classes. You take all of them, which there are infinitely many drawings, and you put all the ones that have only 4 vertices, no edges, in one equivalence class. So think of this as equivalent classes. These are equivalent classes. So any graph that you give me with 4 vertices is going to be in one of those classes. And I'm just taking one representative. And the representatives, because they're in different classes, they're not isomorphic by pairs. Right? We define isomorphic for pairs. So what we're saying is that any pair in here is non-isomorphic. However, you have all the representatives, so any graph that you give me is isomorphic to one of these representatives. Okay?
Yeah, just that interpretation was throwing me off.
No, thank you for asking. I completely get it. Let's see. 1, 2, 3, 4, 5 edges, right? So it should be that one. needs to be that one. And so then you can, if a problem asks you to prove that these two are isomorphic, you can try and find the relabeling. So let's see. This one has degree 3 and that one has degree 3. This one has degree 3 and this one has degree 3. So I probably should label that AB, C, and D. And then check that I really have the node, A joins to B, C, D, A, B, C, D. B joins to A, C, D, A, C, D, and then C joins to B and A, C to B and A, and D to B and E, D to B and E. They're isomorphic. So that's what we're doing. All right. So they're equivalent. They're in the same equivalence class, right? Okay. So, okay. And so you have problems like this, so that these two graphs are not open. Yeah.
How are they isomorphic? Because I thought B is not connected to BC. Well, not exactly like straightforward. Or wait a minute, never mind. Because I didn't see the birthday there. I thought it was because A was in the way. Or wait a minute, because of the arch. Is it because of the arch? So as long as you have the edge is the same for both sides. Or wait a minute. When you said
so you're looking.
The definition of being isomorphic if it has the same number of edges and same number of vertices, right?
No.
Oh.
Isomorphic means that you can label both so that they have the same pairs, the same edges, right? So in both of them, you have A, B, A, C, A, D, A, B, A, C, A, D, B, C, B, D. In both of them, you have those edges.
Okay.
Exactly those. So now they're isomorphic. It's not only number of vertices and number of edges, because if it were number of vertices and edges, then these two will be isomorphic, but they're not. You really mean essentially the same graph, maybe drawn in a different way. So they need to have, same labels. You come up with the labels, same labels, so that they have exactly the same edges. Okay? All right. So, yeah. So, here we show the isomorphism. Sometimes when you want to prove that that things are not isomorphic, it's harder because you need to find something that they don't have in common, right? Like they don't have the same number of vertices, they don't have the same number of edges, they don't have the same degree sequence. And so it also works when they don't have the same cycles. This one here has a C3, a triangle, but this one doesn't. The other one doesn't have triangles, doesn't have C3s. They have the same degree sequence. The degrees are three, all of them, right? All degrees are 3. So they have the same degree sequences. They have the same number of vertices, same number of edges. All degrees are 3. So you won't be able to use that to prove that they're not isomorphic. We're trying to prove that they're not isomorphic. So to prove that they're not isomorphic, you need to find something that they don't have in common. And what they don't have in common in this case is this one has C3s as a subgraph. And this one doesn't have C3 as a subgraph. So they're not isomorphic. They, they need to have also the same number of same size cycles. So if one has two C3s, the other one has two C3s. If one has three C4s, the other one needs to have three C4s, and so on. They have also the same number of cycles inside. Another way that you can prove that they're not isomorphic is look at their complements. So one of them is this, is the hexagon with its diagonals, right? And so the complement is going to be this triangle, right? And that triangle. That's the complement. I'm just going to draw it below, right? So every edge that's not there, it's in the complement. So I'm going to draw it below. So this triangle and that triangle. Yeah. And for the other one, I have the hexagon. And if you look at the complement, it looks like this. I have these two diagonals, and then this part of that triangle, and this ones. Anyways, just draw all the ones that are not there. I'm gonna draw it below. So I don't have these two diagonals, and I don't have this, and I don't have that. Mm-hmm. Now look, this is actually a connected graph. Look, I can start right there and go through the edges and get back to my original place. So that's a C6. This is a C6. However, in this one, if I start in one place, I go like that and I close that loop and I won't be able to get to the other vertices. So this one actually is two C3s, or C3 plus C3. Two C3s. And so this one has two components. They're different. They're not isomorphic. This one has one component, one connected component. They're not isomorphic because of that. They have different number of components. Yeah. Then the original graphs are not isomorphic. Okay. So that's another way that you can prove that they're not isomorphic. Either showing that they have, one has a subgraph that the other one doesn't, or one has more copies of the subgraph than the other, or they have different complements. And different, I mean not isomorphic complements. Mm-hmm. So this is another example where complements are very helpful. And usually, when the graph is very crowded, very dense in edges, you want to look at the complements because the complements are easier to understand. So if I look at the complements, and this time actually I'm going to draw them right here. You see the complement of this one is these two edges. And the complement of that one is this and this. Are the complements isomorphic? Yeah, I also have that vertex.
Yes. Same number of vertices and same number of edges.
It's not only that, remember? You need to be able to relabel them so that they have exactly the same pairs as edges. But it's not only that. In this case, you can see that really, the complement is just one vertex and two edges, right? For both of them. That's the complement for both of them. So maybe drawn in a different way, but you see, isomorphism means that they're essentially the same. And, even though they are drawn in different ways, definitely this vertex goes to that vertex because that's the one that is isolated. And these ones, it doesn't really matter as long as, B is joined to C. So if I decide for this to be B, then this one has to be C. And then, just pick the other two letters. And I just need to make sure that the and E are joined to each other. So there is the isomorphism. So not only the complement helps you decide, and even without proof, you know that the complements are essentially the same, right? They are isomorphic. So you can give the isomorphism. Same, same in everywhere. Like here, we decided that these are not isomorphic, and that's why these are not original ones. But if they had been, and it's easier to see the isomorphism here, it carries on. So if you think about it, we were actually giving the isomorphism for the red one, for the complements, but it is also an isomorphism for the original ones. You can check it.
Right. Professor, just real quick.
Yeah.
So in order to determine the two graphs are not isomorphic, we're gonna see the subgraphs. Is there anything different in the subgraphs? And or the other cases, we're looking at their complement, and we found that one has two components, and other has one component. So that's how we conclude they cannot be isomorphic, and the original graphs are also not isomorphic. Is that how we?
Not isomorphic, right? Yeah.
So is there? That's the only all cases that we're looking at to determine that's not isomorphic.
No, there can be. So let me say this: if I give you two huge arbitrary graphs, it could be really hard. There is no algorithm. This is a very important, you can think, open problem in computer science intersection mathematics. It's really hard to decide if two graphs are isomorphic or not. If you're lucky, you have two graphs that have different number of vertices, and you can say right away they're not. But if they do have the same number of vertices, then you don't know. Inconclusive. Your test is inconclusive, right? And then you go to the number of edges. If they have different number, they're not isomorphic. If they do, your test is inconclusive. You go to degree sequence, same thing. If it's different, they're not isomorphic. If it's the same, you don't know. And you can keep going, check all the subgraphs, check all the triangles, all the C3s. They have the same number, inconclusive. They have different number, not isomorphic. You can keep going. Look at their complements. Well, maybe the complements are also very crowded and it's hard to see if they're isomorphic or not. But if it's easy to see that the complements are isomorphic, then the originals are. If the complements are not isomorphic, the originals are not. So whatever happens to the complement happens to the originals. But chances are that if you have a huge graph, like the ones that data science and computer science works with, chances are that those are very, very hard to decide on anyways. So these are just like a few ideas of how you can decide for small graphs for not isomorphic. But there's no tool. Nobody knows in general. There's no algorithm. There's no recipe. These are just a few tools to decide. Now, if you're lucky to find the isomorphism, then that's it, right? That's the proof. But finding the isomorphism, so it could be really hard. Now, all the examples that you're given are doable. Yeah? They're very small, number of vertices, number of edges. Yeah, but having said that, the problem in general is a very difficult problem in the applications. It's necessary, and we don't have any tools to actually say here it is. Okay, so here, so use complementary graphs to determine which of the 6 graphs are isomorphic to each other. So again, you want to kind of break it into equivalence classes. In this problem, you want to say, I don't know, graphs 1, 3, and 4 are isomorphic, 2 and 5, and then 6 is by itself, or whatever. I just made it up, but that's what you want. You want to find the equivalence classes. Mm-hmm. So, and it says as a hint to use complementary graphs, so we can do that. Here you can see that this vertex is joined to all the ones across, but not to the ones in the same column, right? So here I'm missing these, which is a triangle, that is a C3. And here I'm also missing that one, which is another C3. So that's a C3, and this is another C3. Okay? So the complement of that one is 2 C3s. And then we can look at the complement of the next one. The next one is missing this. So I'm kind of just to be organized, I'm going like one vertex at a time. Is joined to that one, not to that one. So I added not to that one and to that one. So I just go per vertex. So I have that. And I'm also missing these ones. And I'm missing for the top vertex, I'm missing this one and this one. And now I think I have them all. Essentially, you need to have, I have 6 vertices, so together, the blue and the original graph need to have the degree, 5 edges around 1, 2, 3, 4, 5. So you can check that all of them already have 5. So I have all the edges. And so now you want to see if these, what is this complement? Mm-hmm. And so, because it has a small degree, you see how the blue degree is 2 for each vertex, just the blue ones. There's 2 blue ones at each vertex. So it's going to be the union of cycles. It could be 1 cycle, it could be 2 cycles, it's just the union of cycles. And so I can try what I did earlier of highlighting, start at one vertex and start walking and see how far I can get. Right? So I can start right here and go through my graph. 1, 2, 3, 4, 5, 6. So it's actually a C6. I could go back to my original starting point. So that's a C6. And then I can look at the next one. So let's see. This one is missing. I'm going to start with the top left vertex. I'm missing. Let me choose inverted. So I'm missing this. And I'm missing this one. That one's covered. Then from here I'm missing this and that. Mm-hmm. And then for the middle vertices, I'm missing this one and that one.
You have that first one if you're going straight across.
Oh, I have the first one. Thank you.
But they have a cross there, yeah.
1, 2, 3, 4, 5. Thank you, Scott. So we have them all. I always double check because sometimes it's hard to see, like I missed that one. I double check that I have exactly 5 around. 1, 2, 3, 4, 5. And then from this one, I'm missing that. And I think that's it, right? Every vertex has 5 altogether around. So now I'm going to trace again, see what I can get. I can always do that only for the graphs that have degree 2. Okay, so here I go. 1, 2, 3. And I went back to the original. So I actually have 2 C3s. Mhm. So this one is 2 C3s. That's a C3. Oops. So this one is a C3, and this one is a C3. So the complement for that one, it was 2 C3s. For this one, it was a C6. For this one is 2 C3s. So the 1 and 3 are isomorphic. 2, the graphs 1 and 3 are isomorphic, 2 is not. Mhm. Let's look at the next one. I have this. Do you want to keep working on that one? You got it, right? You want to do the other 3 on your own? And maybe we look at a harder problem?
I think number 4 would be 4 of C3s, right?
4 C3s. Let's see. Let's see. 1, 2. I'm missing this one, right? What you talking about this one?
Yeah. Oh no, I probably saw it.
C6.
Yeah. C6.
That takes, yeah. So let's just go a little quickly. Faster, please. I'm missing that one. I'm missing this one. And I'm missing this one. And if you trace it, that's going to give you another C6. I'm going to start here. 1, 2, 3, 4, 5, 6. So that's a C6. And then for the last one, I'm missing this, 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 this. And as you can see, I actually did it in one trace, right? So that's another C6. Mm-hmm. So 1 and 3 are isomorphic, 2, 4, 5, and 6 are isomorphic. Okay? Oh, wait. I know what we are going to do. Give me 1 second. Mm-hmm. Okay. Okay, no, I couldn't find it. Anyways, I have a, you know how we used to have like the activity, the class activities? I have one for isomorphisms. So maybe I can use that instead of the quiz. I'll find it. And then we can do it all together in class. Okay. I think we can do that instead of the quiz, but I'll let you know. Or maybe as the quiz, I don't know, but I'll let you know. Anyways, so you can take a look at the problems and we can stop at some of them and I can give you at least some hints. So here, list all unlabeled graphs with 5 vertices and at most 5 edges. So this, if I ask you for all the ones with 5 vertices, there are many. Like we already took a lot of time doing the ones with 4 vertices, right? So in this problem, you want 5 vertices, but very importantly, at most 5 edges. So you don't have to go. Essentially what they're saving you, because in a graph with 5 vertices, the complete graph has 5 choose 2 edges, has 10 edges. So essentially they're not asking you to, they don't need you to draw the complements. When we did the ones for 4 vertices, 1 second, So when we did these ones, I first started like that, right? And then I drew the complements. They're essentially what they're saving you is to draw the complements. Because, somehow they're there. So they're just asking you to do 0 to 5 edges. Okay? Okay. So use your answer to determine the total number of different isomorphic unlabeled graphs with 5 vertices. So this is all of them. So that would be like what we did for 4. You see, if we had only done the ones up to 3 edges in problem number 4, then we know that all of these come with their complement. And so we could have said, okay, for each of these, I have the complement. So it's this times 2 plus this ones. Okay. So it's the same with the ones for 5. You're going to look for the 0, 1, 2, 3, 4, and 5 edges. From 0 to 4, you can just duplicate because each one has its complement. That's also a representative of an equivalence class. And then you just add the ones for 5 edges. So that will give me the 11. You see, 1, 2, 3, 4 are duplicated. 2 times 4 is 8 plus 3. Because here I have some complementary graphs in this class, in this group of the 3 edges one. Okay. So these are the 2 regular unlabeled graphs with 11 vertices, including no isomorphic repetitions. So it's the same type of problem, but this time you have 11 vertices. Again, making the list of all the 11 vertex graphs, it's huge. So you don't want to, well, not huge, but it will take a really, really long time for 11 vertices, okay? So what they make the problem easier, they're asking you to just find the 2 regular graphs. The 2 regulars are cycles, cycles put together. So it could be like the C6 and the C3, C plus C3. Those are unions of cycles. So these are unions of cycles. And so you want all the ones with 11 vertices. How many can you have? I can have C11, I can have C3 and a C8. I can have C11, I can have a C8 plus a C3. All of those are 2 regular. If you actually draw them, you'll see that all the degrees are 2. And those are the only possibilities. They have to be unions of cycles. So here you essentially have to find like the partitions of 11 into parts that are at least 3. See if you can handle that. Show that all 6 regular graphs with 8 vertices are isomorphic to each other. Draw one of these graphs. You see, when I have 6 regular graphs, so what this means, if you remember, is that all the degrees are 6. And they have 8 vertices. So what's the degree of the complement? What are the degrees of the complement of any graph like that? See, I have 8 vertices. I have 8 vertices, and I'm supposed to have a graph with degree 6. All the degrees are 6. Look, 1, 2, 3, 4, 5, and 6. Did I draw 8 total? There's something wrong in what I did. Wait, let me count. 1, 2, 3, 4, 5, 6. Oh, yeah. It was okay. Degree 6. So, I may have other things. I'm just focusing on this one vertex, right? I'm focusing on just one vertex. So the complement is just going to have one edge attached to that vertex, right? And then for the rest, there, I don't know what else happens in the rest of my graph. There might be, all the vertices need to have degree 6, so there's a lot of edges. But what I want to say is that the degree sequence of the complement is 1, 1, 1, 1, 1. If my graph is G, it has degree sequence this 1, 2, 3, 4, 5, 6, 7. So this is the degree sequence for G, and the degree sequence for G complement then is going to be 1, 1, 1, 1, 1, 1, 1. Right? So we need a graph with 8 vertices and degrees all 1. Can you draw that one? All the vertices need to have degree 1. Okay, so let's draw G complement. Let me just say here we need to have something else, right? So degree 1, all of them degree 1. So now this at degree 1, nothing else can attach to them. Nothing else can attach to it. Nothing else can attach to them. Nothing else can attach to them. That's it. That's the only one, right? So it's easier to understand the complement because this graph is very crowded. This one is very crowded, so it's better to look at the complement. When you look at the complement, you realize that there's only one. So now you can draw the complement of this one to give the picture that they asked you to find. And in fact, you can use that one, but this is isomorphic to also just using the diagonals. So, like this. It's isomorphic to that one. So you can draw all the edges except the diagonals. That's the one that you want. So that one's done. Questions so far?
Just on your degree sequence, wouldn't you have 8 instead of 7 there?
Oh, did I write 7? 1, 2, 3, 4, 5, 6, 7. Thank you, Scott. Yeah, there should be 8.
Okay. I was getting confused with the edges of the vertices thing.
Yeah, so again, they're in red because I didn't have them before, so it pops up.
Thank you.
Thanks. You see how you can come up with many different types of problems along the same definitions, the same lines. Here, show that there are exactly 2 different non-isomorphic 4 regular unlabeled graphs. So for regular, all the vertices have degree 4. With 7 vertices. Draw 1 of each. Okay, so again, the more vertices you have, the less likely it is that you can find like all the representatives as we did for 4, right? So they're giving you more conditions so that you're looking just at a smaller group of graphs, and then you're looking for the equivalent classes that satisfy those properties. So here we have, there are exactly 2, we need them 4 regular, so all the degrees are 4. And 7 vertices, right? So 7 vertices and all of them degree 4. So let's see. Let's use, is it worth it to use the complement? 1, 2, 3, 4, 5, 6, 7. So this time around, we actually have 4. I mean 7 in the degree sequence, right? 1, 2, 3, 4, 5, 6, and 7. Do I have 7? Yeah. So that's going to be my G. And then what's the complement? What's the degree sequence of a complement? 1, 2, 3, and 4. If a vertex has degree 4 in G, then in the complement it has degree 2. Right? So, and again, I'm just focusing on that one vertex. I don't know what else is in here. I'm just focusing on that one. just to figure out what's the degree sequence of the complement. Okay, the good thing is that all the graphs that have, all the degrees equal to 1 just look like this, like separate edges. All degrees equal to are unions of cycles. So this one is a union of cycles. Right? So G complement needs to be a union of cycles, 7 vertices. How many of those there are? It has to be either C7, just one cycle, or if I want to have 2 cycles, it could be C3 plus C4, but that's it. Because the cycles start at 3. I cannot have a C2. It's not a cycle. So the first cycle is C3, so the smallest I can have is C3, and then a plus a C4. And therefore, I cannot have 3 cycles, right? Because I will need to have at least 9. So those are the only 2. Those are my 2 graphs. Of course, these are the complements. So you want the complement of C7 and C3 plus C4, which looks like this. C3, C4, or C7. So that's G complement. So the ones you have are all the other edges. Take the complement. Those are the ones that they're asking you to get. Okay. Oh, and then it says, that's all we had to do for B15. So let me say this was 15 and this was 14. Okay. Let's see.
I have a question. I'm not quite understanding the complement of each graph. Like,
just draw all the edges that are not there. If this is J, actually, let me just read it. If this is your original graph, as I had it there, so a C4 plus a C3, just join with edges all the pairs that are not already joined by edges. So that's going to be the complement. Of course, I'm drawing it on top of it, but in reality, you just don't draw those that are already there. Draw all the others. So, this one was not there. But these two were already there, so I don't draw them here. That's why I usually draw with a different color on top of my graph.
Okay, I see.
And you keep going. So now that one, this other vertex, I don't join it here because that one is there. I don't join it here because that one was in the previous one, right? But I join it to all these 4. And same for this one. And so I'm done with those 3 vertices. And for the rest of my graph, the only ones that I'm missing are these diagonals. Those will be the diagonals here. And then from left to right, everything. From the triangle to the square, everything that goes across, and then the diagonals of the square. So that's my complement. So if this was G complement, this is G, because you can go back and forth. The complement of the complement is the original. Okay.
Professor, just one question for the complement. Can we actually look at the problem, I guess 14 again, B14?
Yes.
So it says show all 6 regular graphs, means all degrees are going to be 6 and has 8 vertices. And we found out that the complement will have all degrees of 1. And for the, I guess, B15, it says,
Give me 1 second, Shane. So here we found that all the degrees are 1, and therefore this is unique. So the complement of any of those graphs has to be this one. Therefore, any of those graphs have isomorphic complements. The complements of any of those graphs are isomorphic, and therefore all the graphs are isomorphic, which was the original question, right? Show that all the graphs with degree 6, 8 vertices are isomorphic. They are isomorphic because all of them have the same complement, or all of them have isomorphic complements. Go ahead, Shane.
oh, I see. But just my
Uh-huh.
intuition, same for 15.
Mhm.
We as Prom said, all degrees are 4,
Mhm.
and we found out that the complement will have all degrees of 2.
Mhm.
And it, for me, this is the part.
Why 4
Oh,
and
with the
2?
7 vertices. Oh,
Yeah, 7
okay.
vertices. Yeah.
I see. So the 2, well, maybe it's not right. By summing 2
N minus
degrees,
1.
we'll have -1 of the vertices.
Yeah, exactly. So if you have n equals 8 vertices, this sum is n minus 1. So here you have n equals 7 vertices. The sum is n minus 1, which is 6, right? And this one is 7. The sum of 6 plus 1, I mean, right? Not the sum of the entire chain, but yes. And that's because the complete graph, this vertex is joined to the others, which there are n minus 1. Okay, so let me just show you. So I'm not going to do any more problems, but I'll show you. So we essentially, hopefully, you can complete fill in the gaps for whatever was missing in these ones. But let me show you the others. This is the last page of the chapter. So these are the only problems that we are missing. For that one, it was showed that they are isomorphic. So here, so try to do this ones. Isomorphic, um, not isomorphic, isomorphic. For this ones, it's the same thing as before, right? So we don't know if all of them are isomorphic or if all of them are not isomorphic. You want to classify them in classes, like we did with these ones, right? So here, the ones that are C6 are isomorphic. So graphs 2 and 5, and the others are isomorphic. 1, 3. Oh, sorry. 1 and 3 are isomorphic. All the others are isomorphic. That's 2 classes. So you want to do the same here. You want to do the same here, and you want to do the same here. You want to classify them. Mm-hmm. So see which of these are isomorphic, put them in a class, and then the possibilities are 3 on the same class, like all of them are isomorphic, or maybe 2 of them are isomorphic and the other one is not. Mm-hmm. And then same thing here. You want to classify them. Here I think you have 3 different classes. I'm not sure. But you want to classify them. Put them in groups, in isomorphism groups, isomorphism classes. Mm-hmm. And and the others are essentially the same, right? Are these isomorphic? Here they're not telling you. You have to find out whether or not they are isomorphic. If they are isomorphic, give the isomorphism. So label them so that they are equivalent, they have the same edges. If they're not, say why. So they should differ in something, right? Like maybe different number of cycles of some size, or different complements, different something. Mm-hmm. And same thing here. So, maybe the 3 of them are isomorphic, or maybe it's 2 on 1. So classify them. So say these two are and this one isn't, or say all of them are, or say none of them are isomorphic. Okay? So, practice. Do you think that you will be able to go over a quiz for this, or maybe we leave it for after Tuesday?
Yeah, I think it's better we leave it after Tuesday because I think not everybody quite understands it yet.
Okay, so let's do this. Go over these problems. On Tuesday, I'll go over questions, but please be aware that because we have the exam the Tuesday after, you're going to have to really, my suggestion is really go over the problems, really know. So we'll have the quiz Tuesday to Thursday so that we can talk about it and you have all answers of everything that you need by Thursday before the exam. Okay?
Okay, so the quiz is still set up for this weekend then.
So the quiz will be for Tuesday, right? I'll open it on Tuesday. It's due Thursday so that we can discuss on Thursday. But instead of this weekend, Tuesday. All right, so you have more time. We can discuss on Tuesday. But then the only downside is that you only have Tuesday to Thursday to go over the quiz. That's the only thing. But I think it's better so that we can go over any questions on Tuesday. All right? Okay, guys.
Okay,
I'll see you next time. Thank you. Bye.
Thank you.